recording. So welcome everyone. Welcome to today's class. Today we are going to start with the radiations. If you have ever see the radiation chapter in a Griffith's book, you will see it's a very pretty long chapter. And even after reading this chapter a lot of times, you will realize that making a good sense out of this chapter is very difficult because there are so many equations in this, and then you have a long derivations, a very much huge amount of assumptions are there. But we have to understand that we are not preparing for semester exams where we have to go for the long derivations. Our goal of this chapter is to understand the basic crux of this chapter, basic physics of this chapter. And I will be covering this chapter in a small dose of radiations. I will giving you the small dosages so that you can digest that, you can make the notes of that, you can do the problems based on that, and radiations becomes simple for you. Okay, and that is a main goal. Today's idea will be to understand what is radiations and then go for a very particular cases in this chapter. Okay, so we will be covering from Griffiths, but only the part which is important, or I will be translating this book very efficiently to you. So let's see what is radiation. Okay, let's try to understand. Just one paragraph we will pick from here. When the charges accelerate, the fields, okay, so here the word comes accelerate. So accelerate is the first word which is coming here. Now what does this accelerate word means? So we know three facts. Number one facts, that if the charges are stationary, if the charge is stationary, then the charge produces electric field, only electric field. If the charge is moving with uniform speed, which basically means that acceleration of the charge is zero, then it produces electric field plus magnetic field. And if the charge is accelerating, means acceleration is not zero, then it produces radiations. And that is what Griffith sir has also said, that when the charge accelerates, their fields can transport energy irreversibly out to infinity. This process is known as radiations. So let's say you have a charge, and this charge starts to vibrate. This is one of the simplest example. You have a charge and it starts to vibrate. When the charge vibrates, it is sort of accelerating because its velocity, the magnitude of the speed is changing, its direction of the velocity is continuously changing. So it basically starts to accelerate. And all of the sudden, it will start emitting the energy. Energy of these radiations will start getting emitted. And finally, what will happen? The vibrations will die out and it will come to the rest. So let's say you have a pendulum. And on this pendulum, I give some charge Q. And I ask this pendulum to start vibrating or start oscillating. So what will happen is that this charge will, as this charge is oscillating, it is emitting the radiations, and finally this pendulum will go like this, and then it will come to rest. It will oscillate. So its oscillations will damp out. Its oscillation will slowly decay and it will come to the rest. So whatever energy this charge had, it will lose that energy to the radiations. It will lose that sort of energy to the radiations. So radiations basically means that your fields are carrying the energy, and this energy is being carried out to the infinity. And that is a basic source. Now, radiation word is very critical here. Okay. So whenever we talk about the energy, we talk about this formula, which is known as the Poynting vector formula. Okay. So this is basically known as a Poynting vector formula. So whenever we say that, okay, something is being emitted, some energy is being emitted, we define number one, intensity. And that intensity is defined by the Poynting vector, and Poynting vector is given by 1 by nu naught E cross B. Any electromagnetic wave or any radiation has electric fields, magnetic fields, and these electric fields and magnetic fields are carrying the energy with them, and they are carrying the energy from one place to another, and energy is going on. Energy is going, energy is going on. And intensity is described. What is intensity? Intensity is energy per unit area per unit time. Per unit time. By the way, today we are going to solve the questions of EM waves. I will do the problems of this Poynting vector in the revision class. I will cover these questions today, and you will learn all of those questions, because I feel that this is important that you learn the questions of this. So after this lecture, when we do the revision class, we will do EM wave questions a lot. So every light has two. Yes, please. Sorry. Yeah. Any doubt? Yeah. Every light has two things. One is intensity. How do you imagine intensity? Okay. You have a laser light. If you bring the laser light very close to your hand, the light is very dark, very, very bright, high intensity. When you take the light away, it is scattered light. So the intensity is less. So if all the
Hello.
light, yes, please. Yeah.
The Poynting vector represents the intensity, right?
Yeah.
Intensity of radiation.
Yes, yes. Yeah.
Okay, thank you.
Poynting vector represents the intensity of radiations. Yes. So, and this is what the idea I'm giving. So if the light has something like this kind of light, and if the light is something like this, so this light is scattered in less area. This light is scattered in more area. This is more intense light. This is less intense light. And how do we describe the intensity? Intensity is described by Poynting vector. You know the electric field, you know the magnetic field. If you do E cross B, you get an intensity. And the direction of E cross B is always the direction in which the wave is going. So let's say wave is going along K cap. If the light wave is going along K cap, for example, in this case, you know the light is going in this direction, then the direction of E cross B is also in this direction. So E cross B has the same direction in which the light is going. One thing. And if I do the area integration, you see, I have done the area integration. Means intensity basically means energy per unit area per unit time. And if I do the area integration, means I'm multiplying sort of area. Area and area cancels, and I'm left with this energy per unit time. Can anyone tell me what is energy per unit time? What is energy per unit? No.
Power.
Hour. Energy per unit time is power. So that is what he is saying here. The power passing through the surface is this thing. You see, this thing is Poynting vector. And if you do an area integration, you get a power.
Sir, power per unit area is intensity, right?
Yes, power per unit area is intensity. So power intensity multiplied by area will be power, right? So you see, this is intensity, this thing, and this is area. So intensity multiplied by area gives you power. Because intensity is energy per unit area per unit time. And if you multiply by area, energy per unit time is known as power. Okay. So let me give these ideas here. So first of all, intensity is energy per unit area per unit time. And power is energy per unit time. So intensity into area gives you power. And this is a formula which is been used to find the power in basic physics or in the basic electromagnetism. I'm not going to use it right now, but this is just basically the power formula we use. And why do we need power? What is the purpose of finding power? Why are we not finding energy? Why we are interested in finding power? Which is more important, energy or power? What do you think? But which of them is a more important parameter? Why power? Why power is more important than energy?
Because it is like a time averaged quantity, and then we can observe time average quantities.
So the more basic reason is that, let's say you go to the market and you buy the bulb. You say that, okay, give me the bulb of 10 watt. You don't say that give me the bulb of 10 joule. You take the bulb of 10 watt, means how much energy it will consume every second. And that is what is important to you. How much energy it will consume every second. If you use it for 1 hour, energy will be consumed more. If you use it for 30 minutes, energy will be consumed less. So energy consumption depends upon how much time you are using it for. But what makes it a bulb? Its power. What is defined for this bulb? The defined parameter for this bulb is power, not energy. Energy will depend upon how much time you use this bulb. If you use the bulb for more time, you get more energy. If you use the bulb for less time, you get less energy. But what is the parameter of the bulb? The parameter of the bulb is power. Power basically tells you how much energy it is giving every second. Air conditioner is using more energy every second. My computer is using less energy per second. Power is different for both of them. Energy consumption, on the other hand, depends upon the number of hours I am using it. So we are always interested in power. We are never interested in energy, because energy is a time dependent thing that will decide how much time you are looking at. But we want time independent thing. Okay? So power is more important. And in this chapter, we will find the power. That is very much important. Okay. So any doubts still here? Okay. Any doubts anyway?
सर
क्या?
जो फिर क्या कहते हैं एटम के अंदर इलेक्ट्रॉन होता है वो रेडिएशन क्यों नहीं प्रोड्यूस करता? अगर वो भी तो एक्सेलरेट करता है.
Bohr-Suri says that, okay. Bohr-Suri says that only in the stationary orbits, even though the particles are accelerating, charges are accelerating, they will not produce radiations because they make a stationary waves, right? De Broglie wave उनका जो है वो क्या बना लेता है? Stationary बना लेता है ना? You must have studied that. कि De Broglie
Yes.
wave, हाँ, तो stationary wave बन जाती है. Stationary wave के समय नहीं emit करता. करना चाहिए था. That was one of the failure of the Rutherford's model, right?
Okay, sir.
Okay. Now, another important part here to understand is this paragraph. The study of radiations thus involves picking out the parts of E and B. So basically, E and B should vary like 1 by R at large distances from the source. For example, in your electrostatics, your electric field is inversely proportional to 1 by R square. It will not give radiations. This is not a radiation because it's an electrostatic field. Electrostatic field. If you have magnetic field, that is also 1 by R square, that will also not give radiation, does not give radiation, because that is static magnetic field. If you want electric field and magnetic field to radiate, then your E and B should vary as 1 by R. So then your electric field and magnetic field should vary as 1 by R. If your electric field and magnetic field are vary as 1 by R, then what will happen is that your S, constructing from then 1 by R square, because then S will be 1 by nu naught E cross B. So then your S will be 1 by R square, because E is 1 by R, B is 1 by R. So then your Poynting vector will be 1 by R square. Okay. So here you can say 1 by R square term in S. And let's say if you integrate them over a large spherical surface, taking R as infinity, then you integrate them with the area. So integration, 4 pi R square. So this R square and R square cancel. So power will not depend upon, power will remain constant. And that is exactly what we want. If you bring out the bulb and that bulb is 10 watt, you want that from beginning to the end of the life, that bulb remains 10 watt. You don't want that your bulb is 10 watt and after some time it becomes 9 watt and then it becomes 8 watt. then it's not a bulb, it's not a good bulb. Then its power is decaying very continuously, and then bulb will die out very soon. So you want whatever energy I have, I should radiate at a constant power. Okay. My power should not depend upon that. So for example, if I'm looking at the bulb from some distance, I can say, okay, this is 10-watt bulb. If I go close to the bulb, still that bulb should remain 10-watt bulb. It should not be like that. I am looking at the bulb and I'm saying, okay, no, it is not 10-watt, it is 5-watt. And if I go close to the bulb and I say, no, it is 10-watt. And if I go more close, I say it is 20-watt. No. So my power should not depend upon R. The power should be same for all the points. If my charge is radiating the energy, then the power of my charge radiation should not depend upon the distance. If it depends upon the distance, then the first line of radiation will fail, because the definition of radiation says that my charges can transport the energy irreversibly out to the infinity. I want to bring my energy to the infinity. But I want, if my charge is accelerating, the energy emitted by that charge will reach the infinity. And that can only happen if the power does not depend upon R. If my power, let's say, is inversely proportional to R, what will happen? As I'm going away from this charge, my power is decreasing, and after some time, my power will become zero. So my radiations will not reach infinity, and the fundamental definition of radiation will fail. So let me again repeat this thing, because this is very important. Once you understand this definition, then we can enter into the chapter. So the point here says that radiation, we can call something as radiation. Basically, this is the fundamental difference between EM wave and radiation. Many students think that EM wave and radiations are the same thing. The very basic difference between EM wave and radiations is that radiations takes the energy to infinity. And if you want to take your energy to the infinity, then your power should not depend on R. So if this is a charge and this is oscillating, let's say, and if I'm here, then also I will say that my charge has a power P. And if I'm here, then still also I will say my charge has a power P. If I'm here, I will still say that my charge has a power P. And if you want that your power should not depend upon R, then your electric field and magnetic field should depend upon 1 by R. If electric field and magnetic field are 1 by R, then the power will be 1 by R. Sorry, Poynting vector will be 1 by R square. And if I multiply Poynting vector with area, I get power 1 by R square, and area is also R square. Then R square cancel. Then my power does not depends upon R. So you don't want your power to depend upon R. That is why your E and B should be 1 by R. And your Poynting vector should be 1 by R square. So this paragraph is very important. Yeah. If any doubt, please ask.
Sir, it means always electric field and magnetic field is inversely proportional to 1 by R in case of acceleration charges, sir?
If it will be, then only the radiations will be there. If it is not, then those are now not the radiation terms. Then
Yes.
those are the non-radiation terms. Yeah.
Okay, sir.
Sir, when do we know that the E and B depend on the distance by 1 by R or 1 by R square?
In a different situations, we do the calculations. For example, I will do the calculations, and from there we get to know that if there will be, so let's say you are finding electric field. One term of that will be 1 by R, one term will be 1 by R square. So you will say 1 by R square is a constant term. On the other hand, 1 by R term is a radiation term. So because of this term, the radiations will happen. So whenever you are finding electric field or magnetic field, you get 1 by R term. Yeah, sorry. Yeah.
Is it like the potential that you studied? Because there are potential 1 by R, 1 by R cube, R to the 4. There are different terms like that. I remember.
Yes, in electric field also there are different terms like that. Yes, yes. Again. And you get those terms by solving Maxwell equations. So Maxwell equations are the fundamental equations that you need to solve. In this case, yeah. Okay. Is it clear? The basic theory. Now I will enter into more of the topic as such. Yeah. Clear, everyone? What do you say? So
Skip.
yeah. So now we are going to skip this topic, electric dipole radiation, because this topic is here to confuse you. We will skip all of this. We will skip all of this. You will also skip all of this. Again, skip, 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 skip. No need, no need, no need, no need, no need right now. No need. Whatever is needed, I will come to this back. And then magnetic dipole radiation. Okay, let's find. Go on, go on, go on, go on, go on, go on. Yes, and reach here. This is a point where I want to focus. General theory. I don't want to discuss the special cases first and then the general theory. Let's first do general theory, and then from that we can talk about the special cases. So the Griffith's book first talk about two special cases. One, electric dipole. Second, magnetic dipole. And then this book talks about the general theory, arbitrary source, any arbitrary source. We will change our order and we will first focus on the general. And then from there we will develop everything. Okay, so that is what your Griffith's book is also saying, that in the previous section we study the radiations produced by the two specific terms, systems. One is oscillating electric dipole and one is oscillating magnetic dipole. No, we don't want to do that. Now what is they are doing that we will do the same process for the charge and current configuration. Charge and current configuration. Okay, okay, let's do that. So what I am excited right now about. So let's say I have any charge distribution, random charge distribution. So this is my arbitrary charge distribution, or maybe there are some currents as well, some random currents, some random charges, and I want to find the power because of this. Okay. So I will not go through the mathematics because that is not what I need, but I need the important steps, that what are the approximations which has been done, what are basically the discussions which has been done for this kind of article. So the number one thing that I come across is this approximation. This approximation says that R dash is much less than R. What does this mean? If you carefully look at the diagram, R is the distance of this point from the origin, and R dash is the distance of any point within the body. So R dash is a vector within the body, and R is so let's say I have this ring. So this will be my R dash, and let's say I want to find electric field or magnetic field at this point, then this will be my R dash. So sorry, this will be R. So R is much greater than R dash. What does it tells you? It basically tells you that the size of body is much less than the distance from the body. So the size of the body is only this much, which is producing the radiations. And where you want to find the radiations, let's say at this distance is much larger than the size of this body. So the size of your body should be very less than the distance at which you are interested in finding the radiations. That is a one approximation. Then all the maths, not my cup of tea, not my cup of tea. I'm not interested. Sorry. And here we come. Let Griffiths do all the maths and let us enjoy the physics. What is we are interested in right now? We are interested in that, okay, this was my any random charge distribution, and this random charge distribution was accelerating. So tell me that what will be the electric field at this point? Tell me what will be the magnetic field at this point, and tell me what will be the power. So the formula for electric field, let's say this distance is R vector. So the formula for electric field at time t comes out to be nu naught by 4 pi r cap dot p double dot. P is the dipole moment, and I have to take the double derivative of that. I have to double differentiate my dipole moment into r cap minus p double dot. This is the formula. However, I will say again, this formula is also not very important. But one thing I want to point out from this formula is that you can clearly see that your electric field is inversely proportional to R. I just want to show you this, that your electric field is coming inversely proportional to R. And the second thing that I want to point out from this is that it also depends upon the medium. it contains nu naught. If it is not medium, it will not contain nu naught. Another interesting fact I want to understand is that it contains dipole moment. It means the radiation occurs whenever your charge distribution have some sort of dipole moment. At least if your charge has some sort of dipole moment, then there is a chances that radiations will occur. And also that dipole moment should be changing. It's not like that the dipole moment of my body is constant. If the dipole moment of my body is constant, then I will not emit the radiations. If the dipole moment of my body is changing, then I will emit the radiations. Because my electric field depends upon P double dash, which is a double derivative of dipole moment. Similarly, this formula results into magnetic field. BRT gives you minus nu naught 4 pi RC R cap dot P double dash. Both of the formula are important. I would say at some time you should remember this formula. Why I am asking you to remember this? You will never use this in the numericals. But once CSIR-NET has directly asked this question, means they directly asked you that which of them will be the electric field. So they directly asked the formula. They directly asked you that, okay, which of them is correct. So it was a formula based question. You just had to tick the right formula. So that is why this formula becomes important. If you want to go through the derivation, I won't say it's suggested at all. Even if you go through, you are going to forget it. So there is no benefit of doing that, right? You have to focus on this formula first. And the three main parts of it. One, it depends upon medium. Two, it depends inversely on R. And three, its dipole moment is changing. And you need to focus on the double derivative of dipole moment. Okay. Now this formula can be written in terms of spherical polar coordinate system. Means you can remove this cross products and you can write your formula in terms of R and theta. If you do that, you get electric field and magnetic field, something like this. Again, nu naught, again, it is inversely proportional to R sine theta by R. So one very important thing here is that it will depend upon sine theta by R. Electric field is along theta cap and magnetic field is along phi cap. Electric field is theta cap. So if it is your sphere, then this thing is phi cap and this angle is theta cap. So electric field is like this and magnetic field is like this. And both of them depends upon two things. Sine theta by R, sine theta by R. Double derivative of P, double derivative of P. Nu naught by 4 pi, nu naught by 4 pi. There is only one C below that. That's all. Because if you want to come from electric field to magnetic field, all you have to do is divide by C, speed. So interestingly, we have our electric field, we have our magnetic field, and we can find our Poynting vector. Poynting vector is 1 by nu naught E cross B. And if you do that, nothing, you can just multiply both of them and you get, so nu naught square is nu naught square, and then you have one nu naught in the denominator, so you get only nu naught. 4 pi becomes 16 pi square, it becomes C, you get double derivative, double square of P double dot, and then you get sine square by R square. So this is your Poynting vector, and this is also very important. And if you do the integration to find the total power, because if you want to do the power, you have to do the integration of S into dA integration. And if you do the integration, final result that you get is this. And this is the most important result you need. T radiation is equals to nu naught by 6 pi C P double dot square. If you know this result, then everything else can be forgotten. Okay. So 4 relations I need from you. One is this electric field and magnetic field, because direct formula can be asked. So this will not be used in numerical. This will not be used in numerical. These two can slightly be used in numerical. This is just a multiplication of these two, so nothing else is there. But this formula will be very much used in numericals. Okay. So these are the relations you should worry about. That when my charge is accelerating, I know electric field, I know magnetic field, I know Poynting vector, and I know that what is the total power it will radiate. And now I can use this formula for any specific system. Yeah. Any doubts you have now, please? Because since we have to find it for some retarded time, because radiations take some time to reach. because by the time your electric field signal reaches that point, your charge configuration has been changed. So you are not interested in what is right now. You are interested in what was the time when it was emitted. So relativistically, you have to talk about the things. Na? It takes some time for light to reach. That is why. That is why you see there is a T minus R by C here. But does
Sir,
not concern as much. Yeah, please.
I wanted to understand like how did this P quantity like
How does
entered into the picture? Like
how does this dipole moment quantity enter into the picture? This you are saying.
yeah.
So whenever the charge accelerates, you can assume it to be a oscillating dipole. Why I'm saying this? Let's make a picture. So let's say my charge was here. It was sitting peacefully. And all of a sudden, this charge decided to accelerate. Like this. It is like start going like this. Now, what is happening here is that, okay, so my charge is accelerating. So this charge at this point will reduce and the charge will appear at this point. Let's say, let me make an image after some time. So now image will be, charge will no longer be here, but the charge will be here. And the image in somewhere between will be charge is here. So my charge is sort of accelerating. And my oscillating charge, if you do the mathematics, you will come to realize that my oscillating charge has a behaving like a changing dipole. My dipole is continuously changing as dipole moment is changing because location of the charge if continuous change, then the dipole moment is continuously changing. It's sort of okay. Let me give you a better visualization. This might not be the good. Okay, let's do two problems and then you will automatically get this visualization that why this dipole is coming as such in the image. Okay, and why oscillating charge is behaving as if the dipole is changing. Yeah. Okay. Yeah. Any doubt as such? Anyone numerical? This way formula wise. Although this was not much of understanding, but let's.
Sir, what is the T0 there?
Yeah. Sorry. Yeah.
So what is the T0 in the formula? P rad, the T0.
Where is it?
So the bottommost formula, sir. Please go down.
In this?
So T0, what the T0 there in the formula?
Last formula.
Yes, sir.
T0.
Yes, sir.
The starting time. Time when you begin. Yeah.
So the power, sir, the power is dependent upon the time, sir.
Yeah, it can depend. It can depend upon time. Yes. It can depend upon time. But not on the distance. It can depend upon time, but not on distance. Yes. You see, there is no R in this. Okay. There is no R in this. Okay. So now I will discuss two problems and you will get much realization that what I'm talking about. Number one is rotating dipole, which is a very important problem for us. So you have a dipole kind of situation. First of all, you have a minus q in the middle and plus q like this. So you have dipole. So dipole is something which has a negative q charge and positive q charge. And the separation between them is, let's say, capital R. Then the dipole is defined as charge multiplied by distance. So charge is q and the distance is r. So the dipole moment is q into r. So I have a dipole and now this dipole is rotating. This dipole is rotating. And it is rotating with an angular speed omega. Okay. And I want to understand what is the power which is being emitted by this dipole, this rotating dipole. How much power this rotating dipole is emitting. Okay. So first of all, let's find the magnitude of the dipole moment. So magnitude of the dipole moment is q into r, which makes sense. Charge into separation between them is radius, whatever is this r, this distance capital R. So the dipole moment is q into r. And let's say at any time you are at angle theta. So if you try to write the vector, you will get cos theta I cap plus sin theta j cap. And how do you decide this theta? So you know that when we are talking about the linear motion, you have displacement equals to speed into time. But when we talk about the rotation, the displacement becomes angular displacement theta Linear speed becomes angular speed omega and time remains time. So theta is basically omega t. So in time t, how much angle it will rotate? It will rotate omega t angle. And let's call this QR as P naught. P naught. Just a symbol. So we write Q naught as P naught and we write cos theta as cos omega t I cap plus sin theta as sin omega t j cap. Now, in order to find the power, what I'm interested in is to do the double derivative of that. So I will do the double derivative of my dipole moment and I will get P naught. If I do double derivative of cos, I get minus sin and again I get cos back. So I get cos, but there is a negative sign now. And if I'm doing it differentiation, then omega will come out. And if I'm doing differentiation 2 times, 2 omegas will come out. So I will get omega square. Because differentiation of cos omega t is omega minus omega sin omega t. And if I do differentiation one more time, I get minus omega t. Similarly, doing the differentiation of sin omega t gives you minus omega square and sin omega t back. Okay, so this is my P double dot. Now, if I want my power, again, I need the square of this. So let's square of this. So if I do the squaring of this, this becomes omega 4, this becomes P naught square, and this becomes cos square omega t plus sin square omega t, which is obviously 1. And this thing becomes P naught square into omega 4. Now we want to know the different things. So number one thing that I'm finding is Poynting vector. So let's go to the Poynting vector formula. So the Poynting vector formula is nu naught by 16 pi square c. Basically, I'm using this formula. So if I use this formula of Poynting vector, I already know what is nu naught by 16 pi square c. I have calculated what is P double dot square. I get P naught square into omega 4. And I also know what is sin square theta by r square. So my Poynting vector is inversely proportional to r square and it is also depending upon the angle. For example, let's say this is the charge who is radiating, then the S vector here will be different and S vector here will be different and S vector here will be different because it also depends upon the angle theta. Okay. And obviously it also depends upon the distance, S vector. And this X vector is radial, R cap, which basically means that your charge or your dipole, oscillating dipole is radiating in the radial direction. In the radial direction. Okay. So this is one another thing. So we got our Poynting vector and in CSIR-NET, I will not be surprised if they ask you exact same question. They give you the oscillating dipole and they ask you what is the Poynting vector. They can ask you because CSIR-NET is repeating the questions from Griffiths and EMT is nothing but a Griffiths. And I have not taken this formula from PYQs, but from the Griffiths. So this question can be repeated directly. Maybe not, but there is a huge chance. Okay. Then we can also find the total power radiated, that how much power your oscillating dipole has radiated. So you will use this formula, nu naught by 6 pi c into P double dot square. So you already know nu naught by 6 pi c, and this you have already calculated how much P naught square into omega 4, P naught square into omega 4. So you have calculated the total radiated power. So this is the first problem, which is basically rotating dipole. Any doubts, sir, please, in this problem?
Sir, P naught was dependent upon time, sir. How you just wrote it, just P naught.
Sorry, this P naught.
But P naught, sir, it is dependent upon time, right? The power is dependent upon time. So there is no time factor here.
No, in this case, I'm saying it may be. I'm not saying that it is always. It could be. In this case, it's not. Okay. Also, this formula is at T naught time. This formula which I'm using is at T naught time. So in the formula itself, I have only restricted myself for finding it at the one time. Okay. I'm not looking at the time evolution of the power right now. Where you are talking in this step, you have maybe in this step you have a problem, or in
No,
the
sir,
last one?
I'm asking the last formula. The
Yeah,
last statement. The P rad you wrote, there is no time factor there, so I'm confused now, sir.
So what they have done is, okay, they have done the time averaging before. So if you look at it somewhere, so power passing through the, so here here everything was in time. Everything was in time. And then they did the time averaging. They did the, when they were doing the integration, they already have done the time averaging somewhere here. So we are restricting ourselves to one time, T naught. One time. Time is fixed quantity here. Time is not changing. Okay.
The time is fixed here, right, sir?
Yeah, here in these questions, time will be fixed. In your entire syllabus, time will be fixed. No, don't worry about the time.
Sir, could you
Yeah.
repeat what is the difference between radiation and EM waves, sir?
What is the difference? Okay, so in radiations, what happens? Your energy is being carried out. But for EM wave, there is no such restriction. It could be carried out, but there is no such restriction. For example, time varying electric field, time varying magnetic field. So for example, okay, let's take an example like this. Your electric field is 1 by r square. Your magnetic field is 1 by r square. In general, when we do the EM waves, and your Poynting vector comes out to be 1 by r4, and your power comes out to be 1 by r4 into r square, and your power depends 1 by r square. So power because of EM wave could be changing. Close to the source, the power could be different. Far away from the source, the power could be different. EM wave is also carrying the energy with them. But in order to qualify as a definition of radiation, you have to understand one thing, that your electric field and magnetic field has to vary by 1 by r. If this happens, then only you say that this thing is radiation. Otherwise, no. Otherwise, no. No, it is not radiation. If it is 1 by r, B is also 1 by r, then it is radiation. That
Sir,
is a
in
one.
terms of radiation, how do you energy? How do you understand, sir? Again, could you explain again?
Sorry, in terms of.
Sir, in terms of carrying energy to the infinity, sir, you just said radiation is a special case of.
No, radiation is not a special case of that. But if you see, if the power is changing with the distance, so close to the source power is more, away from the source power is less, even more power is even less. So ultimately your power will die out. So your radiation does not have a capability to reach to the infinity. But in this case, the power is not depending on R. So here also, if this is a source, here also the power is that much. Here also the power is that much. Here also the power is that much. So your radiations will ultimately reach to the infinity. So radiations basically means that which carry out the energy from the source to the infinity. And just lose, as a result, this source will lose everything, all of its energy, whatever it has. But when we generate an EM wave, this source is transferring the energy, but it does not mean that this source is losing some sort of its energy. For example, when you have a charged sphere, it is also emitting electric field. And that electric field is basically kq by r square. It is emitting the electric field by kq by r square, but it does not mean that your sphere is losing something. It is emitting electric field, not emitting, but it has an electric field, but it does not mean that it is sort of losing some of its energy. No. But let's say if this sphere have an electric field which depends upon kq by r, then this will represent somehow that this sphere is emitting some of its energy. The energy of this sphere will somehow decrease, and it is emitting that energy into this space around it. That is the difference. In EM wave, when you emit an radiation, it may or may not be loss of energy for the source. But in radiations, when the radiations are being emitted, it is the result of loss of energy for the source. Source will lose its energy and give it into the radiation. That is also the core difference. And that whenever you see electric field is 1 by r, source will lose its energy and give it to the radiation. Let's see how the CSIR-NET has asked this question.
Hello, sir.
Yeah, please.
सर इन एटॉमिक मॉलिक्यूलर फिजिक्स में जो क्लास लिए थे आप, उसमें एक बताए थे कि जब ईडी आएगा तो आप बताएंगे कि why vibrational and rotational spectra only given by dipole molecules.
Why?
Uh,
See, you see this reason. Yeah, dipoles are, you see the dipoles are vibrating, right? Dipole, whenever the dipole changes, oscillating dipole, na, vibration in this, what happens? Dipole movement change. In rotation also the dipole, rotation basically means what is rotating dipole. And when the rotating dipole happen, radiation is emitted, right? You connected it to a very nice place. What do you say? In dipoles have, what does dipoles have dipole moment, right? And if that dipole starts rotating, for example, in this case, so you get a radiations, and those radiations are seen in the rotational spectra. Similarly, if the dipole starts vibrating, again the dipole moment is changing. Again, it will emit radiations, and that radiations will be taken in the vibrational spectra. But let's say this system does not have any dipole moment. Then the how you will emit the radiations? What do you say? Then we go for Raman, right? Right? What do you say?
yes, sir.
Yeah, very good. Nice connectivity. Right. Let's see how CSIR-NET has asked this question. So CSIR-NET says that a particle with charge minus q moves with a uniform speed omega in a circular orbit of radius a. So let's say this is a circle of radius a. This is a circle of radius a, and minus q is rotating, and plus q is at the center. Okay. Now they said let the intensity of the radiation at this point be I1. So this point is on the z-axis. So if this is the circle, then this point is the first point, and this point is the x-axis. So this is an x. So if I make the x, y, and z. So the first point is here, 0, 0, r, and the second point is here, 2r, 0, 0. So intensity at this point is I1, and intensity at this point is I2. Now I want to ask from you, does intensity depends upon a distance? Power does not depends upon distance, but does the intensity depends upon a distance?
Yes.
Yes.
Yes, sir.
Why? Because intensity is a Poynting vector, and Poynting vector depends upon r. Okay. So the same problem as before. It's a oscillating dipole. And what was the Poynting vector for oscillating dipole? We found like that. And you can clearly see that it was along the r cap. So you see nu naught. So let me be very clear with this. Nu naught p naught square by omega 4, nu naught p naught square omega 4 divided by 16 pi square c, 16 pi square c, sine square by r square, sine square by r square, and then you have r vector. In the first case, I want to find my intensity at this point, and this is z-axis. So what I will do r cap dot j cap. What is r dot cap dot j cap? So this is your r vector in spherical coordinate system. This is your z vector. What is an angle between r and z? You tell me. Theta. This is how we define the theta. Theta is an angle between z and r. So if you do r dot j, you get the magnitude of r is 1 because it's a unit vector. Magnitude of j is 1 because it's a unit vector, and you get cos theta. That is why you see a cos theta here. That is why you see a cos theta here. Okay. Now I'm just making this rough diagram on this side. So this thing is a capital R, because you see the distance on this z-axis is capital R, and this thing is a capital R. And now okay, so let me give you a good visualization. So this thing is rotating like this, and you are interested in finding the Poynting vector here. So this thing is R, and this is a radius. So this is A. So this thing is A, this thing is R, capital R. You can clearly see. So your electron is, or your negative charge is rotating like this. So this thing is A. If this is A, then this is also A, right? Parallel lines. And this thing is a distance on the z-axis. How much distance on the z-axis we have? Capital R. So I just make this diagram. This thing is capital R, and this thing is A, and this is R cap, and this is J cap, and this is theta. in our formula, you see one is sine theta and one is cos theta. So if I do sine theta, I will get perpendicular, which is A, into hypotenuse. So this thing will be A square plus R square under root. Similarly, cos theta will be base by hypotenuse. Now it is given to us that R is much greater than A. If R is much greater than A, then this thing will simply become A by R. And this thing will become R by R, which is almost 1. So cos theta is almost 1, but sine theta is A by R. Okay, sine theta is A by R. So what do you get then? Sine theta is A by R, right? Perfect, right? Yeah. ठीक है. So A by R. सही हो गया ना? So then if I do this, if I put in this, isn't it cos theta should be A by R? Base cos theta is, if this is grand, then this is almost equals to 1. And sine theta becomes perpendicular, which is A, and then divided by this distance, A square plus R square. Okay. And then we had this R square as well. So then it should become 1 by R square should already be there. And if I do sine square, it should be A square by R square, right? It should be then power 4. Okay. Just a second. Something is fishy here. Sine theta, sine phi. Sine theta is A by R. It should be A by 4, A by 4. What I am missing here? Should be R cube. As I remember, it should be R cube. S dot J. Sorry. S dot. Okay, sorry. Here I made the mistake. Sorry. So it is S dot J. Basically, it is S dot R vector. And what is your R vector? Your R vector is, this thing is capital R into J cap. Okay, capital R into J cap. So this thing will be R S dot J cap. So there should be one R here as well. You want to know, but won't this change the units of that? I should be multiplying with R cap, right? I'm multiplying with R cap, because if I multiply with J cap, okay, I will bring this question back, okay? Because while doing it, I got some confusion in this. I think I am missing one R factor somewhere. Yesterday, I thought it is correct solution, because its solution you will not find anywhere. This is a theory I was trying to build in that, because this question connects with this directly. Everyone you say, you will directly see that intensity depends upon R cube, but no one has given the reason that why intensity depends upon R cube. So I was trying to build the reason for that. Okay, we will come back to this question again tomorrow. Okay, for now, let's stop for this question. Let's move to next question. Okay, tomorrow we will come to this. Next question is really interesting. And this question, I think, can be asked in the future, because it's a Griffiths problem. And many times I've seen CSIR-NET is asking direct question from the Griffiths. And this question can be asked as such in the future. And let's see what is this question. So let's read this problem. And this problem we will do it's a very important. We have an insulating circular ring, and the radius of that ring is B. It is centered at origin, and it carries a linear charge density like this. Okay. So we have a ring. So this is the ring you see here. First of all, this ring has a linear charge density. So means the charge is everywhere. But the problem is that somewhere the charge is more and somewhere the charge is less. For example, when the phi is 0, the charge is 0. So there is no charge here. But when the phi is 90 degrees, the charge is maximum. So the maximum charge is here. Then again, there is no charge here. Again, the charge here is maximum. But here it will be now become negative, because sine 270 is negative charge. So you see here it is positive, 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 positive. negative, 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 negative. The charges are maximum on the equators and it is 0 on the axis. So this this ring is something like this, charged like this. So sine 0 is 0, sine 180 is 0, sine 90 is positive, sine 270 is negative. Okay. In the first and second quadrant, the charge is positive. In third and fourth quadrant, the charge is negative, because sine is negative in third and fourth, sine is positive in first and second. So upper part of the ring is positive and lower part of the ring is negative. So the very first step is to let's find the dipole moment. We can convert everything into dipole moment. So this ring will have some sort of dipole moment. And then in the next step, we say that now the ring is set to spin. So then we say, okay, let's start spinning this ring. So when the ring starts to spin, so let's say I find that dipole moment of this ring. So let's say that dipole moment comes like this. And now all of a sudden I start spinning the ring. So now this dipole moment is rotating. So this becomes the same problem as before. So now this problem has two parts. First part is to find the dipole moment of this ring. Second part is once the dipole moment is found, start rotating this dipole. So the first step is to find the dipole moment of this ring. And how we can do that? This question is from this part. This is basically from the electrostatic part. How we can do that? So you say Q into D. If it is a simple charge and the distance, so if it is something like this, minus Q plus Q and the distance between them is D, then the dipole moment is simply charge into distance. Dipole moment is charge into distance. But let's say you have a system like this, one charge here, one charge here, one charge here, one charge here. Then you do summation of Qi into Ri. Summation of Qi into Ri. Find the Qi here, Ri vector of this, Qi charge of this, Q1 into R1 vector plus Q2 into R2 vector plus Q3 into R3 vector plus Q4 into R4 vector. And this gives you dipole moment. But let's say you have something continuous body like this. Then you take a small charge dq, you find a distance, and basically it becomes R dq integration. R dq integration. That's all. So you have to do R vector into dq integration. So some
Excuse
q
me, sir.
becomes, yeah, sorry. Yeah.
I just missed the part, sir, where you told that the ring is a dipole. Can you explain how the ring is a dipole?
How this
Sir,
is?
how the ring is a dipole, sir? Could you please explain again? I just
Ring
missed
is
that.
not, no, ring is not a dipole. Upper part of the ring is positive, lower part of the ring is negative. So ring becomes a dipole, right? Dipole means the two charges separated, right? Plus and minus. What is dipole? Dipole has two charges. One side is plus Q, another side is minus Q. In our case, in which the lambda is given like this, if I say, okay, this is your ring and everything is positive, then this is not dipole. Or if I say everything is negative, then also this is not dipole. But in our special case, because you know the sign is positive in first and second quadrant. So you see in first two quadrants, the charge is positive. But in third and fourth quadrant, the sign is negative. So the charge is negative on the lower quadrants. So upper part of the ring is, yeah. Clear? What do you say? So upper part of the ring is positive, lower part of the ring is negative. So overall, your dipole is having some dipole moment, and we are trying to find that dipole moment. So I just replace this q into small dq, and r vector remains r vector, and then I do the integration. Okay. So this dq is here, and let's find this r vector. This r vector will be cos phi I cap plus sin phi j cap. And how will you write r vector? The magnitude of r vector is r, and the direction will be cos phi I cap plus sin phi j cap. You see here. And then you have dq. I already explained in the last revision class that if you have one dimensional body, how do you write dq? Lambda into dl. If you have two dimensional body, you write sigma into dA. If you have three dimensional body, you write rho into dv. It is a one dimensional body, so we write lambda into dl, lambda dl. How do you write dl? If this is small length dl, and this is radius r, and this is small angle d phi, then dl can be written as r d phi. So lambda dl becomes, lambda is lambda, so let's put the value of lambda. Lambda is lambda naught sine phi. dl becomes r d phi, and there is this r also, this r also. So this r and this r becomes r square. This lambda naught comes out. Then you get cos phi into sine phi, integration with d phi, and then you get sine phi into sine phi, integration with d phi, and your integration goes from 0 to 2 pi. Can anyone tell me that what will be the value of this integration?
0.
0. Q? Why? So
The odd function
So
into
odd
multiplying
function.
odd function, right? Cos is
Even
a even,
function.
sine is a odd, so odd into even becomes odd. So it's an odd function. So if it's an odd function, then its integration is 0. However, its integration will be pi. Integration of sine square phi or cos square phi from 0 to 2 pi is pi. You can calculate that. I hope this much integrations you can do. So this thing will be 0, and integration of this thing will be pi. And there is lambda naught r square outside. So I get lambda naught r square pi j cap. So this is my overall dipole moment. I have not started rotating the dipole yet. I'm just saying that, oh, yeah, please, sorry.
Sir, could you repeat how to do integrate, sir?
Sure. So you see, very simple. Let me do this. So let's say you want to solve this integration. One is doing the full steps. One is cos phi into sine phi into d phi. If I multiply divide by 2, I get sine 2 phi into d phi, 0 to 2 pi. Sine 2 phi becomes cos 2 phi divided by minus 2, going from 0 to 2 pi. Cos 2 pi is also, so this becomes minus 1 by 4. Cos 2 pi also becomes, so this is cos 4 pi minus cos 0. Cos 4 pi is 1, cos 0 is also 1, 1 minus 1 is 0, so this integration is 0. Also, there is a short trick that cos phi is a even function, which basically means if you have cos of minus phi, it is equals to cos phi. Negative does not comes out. But if you put sine of minus phi, it becomes minus sine phi. So this is an even function. Sorry, this is an odd function and this is an even function. Odd into even is odd. And whenever you do an integration of odd function in a full cycle, 0 to 2 pi, then the answer is 0. And that is a direct result that you get from the Fourier series. You do such integrals in Fourier series. Then you have to do an integration of sine square phi. Now, in order to do that, you use this formula that cos 2 phi is equals to 1 minus 2 sine square phi. Then sine square phi becomes 1 minus cos 2 phi by 2. I hope that now you can do an integration. Half will become phi and cos 2 phi will become sine 2 phi, and then you put the limits. Okay, so this
Sir,
is how.
thank you, sir.
Yeah. So this is my dipole moment. I have not yet started rotating the dipole. I am just saying that this ring has a dipole moment given by this. And I will give you the visualization of that. So let's say this was a ring. Upper part is positive charged. Lower part is negatively charged. So the dipole moment is from negative to positive. Similarly, here the negative dipole moment is from negative to positive. Here also the dipole moment is negative to positive. This thing is already along j cap. If you break its component, one component you get in this direction, one component you get in this direction, they cancel out. However, the vertical components adds up. So you see the vertical components of all the dipole moments are adding, and horizontal components of all the dipole moments are cancelling. As a result, the net dipole moment is along j cap. And that is exactly what we get. Again, I am repeating, the upper part was positive, lower part was negative. This is negative to positive, this is negative to positive, this is negative to positive. If you break the components, one is the horizontal components which cancels, and one are the vertical components which adds up. So all the vertical components are adding and all the horizontal components are cancelling. So the net dipole moment is along j cap. What do you say? Right? And that is exactly the result we got. So this is our P naught. Before rotating, what was our dipole moment as such? P naught. Now let's start the rotation. Then goes the same mathematics. You know, P vector is P naught into cos omega t I cap plus sin omega t j cap. Now it is rotating. Now, if you do the double differentiation, you get minus P naught omega square cos omega t I cap plus sin omega t j cap. You do the square, you get P naught square omega 4 cos square omega t plus sin square omega t. You get P naught square omega 4. And then you use the formula of total power radiated, what is mu naught by 6 pi c P naught double dash square. And you put the value of this, you get P naught square into omega 4. And then I bring this value of P naught. And this P naught is what? Lambda naught r square pi. So lambda naught r square pi. If I do that square, I get lambda naught square r4 pi square. And then very simply, I can cancel pi with 1 pi. I get mu naught pi lambda naught square omega 4 r4 by 6c. This is the total power radiated by this problem. So the steps in the problem will remain something like this. First step, find the total dipole moment. Second step, do the double derivative. Third step, square it. Fourth step, use the formula of power and put the value of that. P square, that's all. P double dash square. And you get your total power radiated answer. So these two problems of the Griffiths we discussed, very important problems, could be asked in an exam. One out of the sight advice I would give you, radiation is not a chapter on which you can rely on. I would say radiation is very good to understand. I have also done radiations when I was preparing for my NET exam. But radiation is sort of something, if it comes from your knowledge, it's good. You can do the problem because this problem can directly be asked in the exam. But if they twisted it, then the theory is so vast for radiations that you will not be able to solve the problem. So I would say restrict yourself in radiations, spend minimum time in radiations, and whatever we covered in today's lecture and one more lecture I will take, let's stick to that. In waveguides, I can guarantee that, okay, whatever I taught in waveguide, nothing will come out, because in last 10 years, if nothing has come out of it, then why this year something will come out? But in radiations, the theory is so widespread that every year the new question is seen. And that is why I say that we will prepare for radiations, we will have the basic knowledge of it, but question wise, we cannot rely on it, right? So that is one suggestion I will always give to you. So in the next lecture, I will discuss some more important parts of it. And I will end my session here. If you have any doubts, I am open for your doubts.